Analysis takes a trace of a program and then it predicts a concurrency bug. And the way it does that is that it looks at the trace and then it says that was executable, and then it predicts a different trace that's also executable and has a bug. So even if the first thing didn't have a bug, the second thing has a bug. And in this setting, soundness means that actually we always predict a bug. And we always have true positives and we never have false positives. And so that's what soundness means. And my question here is, how do we define soundness and how do we reason about it? And what I want to persuade you today is that we have generalized all the previous work and we have used that to do something new, which I will tell you what is. And there is a lot of previous work. There's a whole bunch of algorithms for predicting concurrency bugs in this way. Many of them predict data races, and many of them work for the setting of sequential consistency. So for example, the first paper there, Fast Track, that's Flanagan and Freund from PLGI 2009. Further down we have M2, that's Andreas Paulogiannis from POPL 2020. RV Predict is the one by Shuyang, Meredith, and Rosu from PLGI 2014. And then the one I really am interested in for this talk is the one at the very bottom, Huang and Huang from OOPSLA' 2016, which works with TSO, the x86 total store order, and so a weaker memory model than sequential concurrency. Many of these have proofs of soundness, but that last one doesn't. And it's going to be much harder to do it when it's not sequential consistency, when it's weaker than that. That's our goal, is to get there. The way these things work, many of them, is that they have the idea of saying, we got a trace, we want a trace that exposes a bug. And the way we're going to do it is we're going to reorder the input trace. And they have so many definitions of reordering, and the idea of it is to say, we have this trace, we don't know the program, we are working without the program that produced it. So what we will do is that we will say, we will only reorder in such a way that every program that could have produced this trace will also be able to produce the reordered trace. And so all these definitions actually form a whole little hierarchy. And what we are after here is an even more powerful definition of soundness that subsumes all the previous ones. And then once we are there, we are then going to take on working on proving correctness for this one for weak memory. And this brings up a question that must be addressed at this point, which is over here on this side, we have the world of predictive analysis. And in that world, they talk about traces, like I have done until now. And on the other side, we have the world of weak memory, because we want to get to TSO. And over there, a lot of the work talks about graphs. So we have execution traces, execution graphs, and it's just not the same. What do we do? And so we looked at that, and we decided to go graphs. And so in the rest of the talk, it's going to be execution graphs, and it turns out to be a very good choice. So all we need is to get the predictive analysis to go along with us and go to the world of execution graphs, and we will be good. And so just to give you a sense of what these graphs look like, here we have a program, 2 threads in the gray boxes, and then I show some snippets of execution graph to the right of the boxes. And so we have a node for every assignment statement, and then we have these program order edges between them. And the thing to note is that the reads, they come with, these R nodes, they come with values of what is read. And we can think of the graph together here as almost a question of saying, can this graph actually be an execution of this program? And sometimes the answer is yes, and sometimes it's no. And it really depends a lot on which values are put there. In this case, 2 zeros. Is that possible? Is it not possible? And it turns out that if we fill in some more memory consistency edges, according to, we could do it and look at it from the point of view of sequential consistency, the answer is no. This program is not a possible execution of the program. And we could also do it and look at it from the point of view of TSO. And in this case, yes, this execution graph is a possible execution of the program. And so that's something we just need to be aware of and take into account when we then start to reason about these predictive analysis. So I will leave it at that and simply say, from here on out, I'm reinterpreting this picture such that the things at the bottom there are execution graphs rather than traces, but otherwise the story is the same. We observe an execution graph, and then we want to predict another execution graph that exposes a bug. We want it to be executable, and we certainly want it to work with the memory model that we have in mind. And so here comes the mathematical version of that. I'll just read through it a little bit. So starting from the top, for any program, well, we don't have it, but for any program, for any program P, we're looking at an execution graph that's a valid execution graph and consistent and everything for that program. And then we have some kind of prediction that predicts a bug. And what we are doing here is that second line, we need the existence of this. It's usually called a witness graph that has 4 properties. Number 1, it has something to do with a bug. Number 2, it's well-formed. Number 3, it is actually executable by the same program. And number 4, it is memory consistent with whatever memory model that we have in mind. And what you should notice here is there's only one program involved. So this story about we don't know what the program was, so we need to take the intersection, or we need to think about for all programs that could have executed this this thing, we need to just be sure that whatever we're going to do works for all those programs. In this case here, there is only one program. And so then you can say, how can we produce, we only know one execution, we don't know the program. How could we ever think of another, in this case, execution graph and know that it is executable? This is where we pick up an idea from the RV Predict paper from 2014. And what they do there is that they have a notion of state similarity. And so what they do is that they say, we don't need to tinker too much with the states, we just need to tinker a little bit so everything stays executable. And the main thing that they tinker with states there, the similarity measure here, is that they take some values and replace them, some actual values, and replace them with symbolic values. And that turns out to be enough to do a lot. And if you do this in a disciplined way, you will stay executable. That's an idea that we pick up, and then what they do is that they have a notion of similarity of traces, and we change that and lift it up to be similarity of execution graphs, and then we are good to go. And so that way we can get stories like this one here, where let's say we observe the execution graph on the top. We have 7 nodes, there are all kind of edges because all the different memory consistency edges are there. And now we can predict various executable graphs, and I show one in the bottom left corner, one in the bottom right corner. And so you can see sometimes we keep as many nodes, sometimes we have fewer nodes. And you will notice if you start looking around that some of the values have been replaced by symbolic values. And so we do this in a very disciplined way so that executability follows. And that now gives us enough flexibility that we can start to predict bugs. So then various algorithms have various things they want to say, and we can reason about correctness. We can reason about soundness. And the way this works in practice is something where we discovered that we have a single recipe that works for all the ones that we tried. And the recipe goes as follows. So first we construct this graph that was like exist graph, the one to the right, we construct that. And in the beginning, we simply focus on the program orders. So we construct all the nodes and then the program order edges. And then we check the free conditions that we have the bug there, it's well formed according to whatever conditions we have, and it's executable. So we get all that done. And number 2, then that's where we insert the memory consistency edges. We do it in a way so we preserve the well-formedness of the graph, and we check that indeed this is memory consistent with whatever memory model that we are using. And then in case we have actually used some symbolic stuff in the graph, the third step is then to concretize that to all be concrete, so that we end up with a concrete graph, which is what the soundness statements requires. And so we use that to prove 6 of the analysis correct, and the highlight is in the third line, this MCR TSO that works with weak memory. We proved that one correct. And actually, it does not take very much space. So our paper is not that long, it's standard length, and we have the proofs of all of these 6 in the paper written in detail. And that's because this 3-step recipe really works. And we give the details in the paper, and I just want to give you one example. This is the full proof of actually the very first analysis that I had, the one from Fast Track. And if you could read this, you would notice that there are a few lemmas in there, and those are lemmas that are fairly general. We use them again and again across different analyses, and so it means that what's new is pretty much here. As you can see, it's not that many lines. So we can easily do that 6 times in the paper and cover a lot of ground. And so in conclusion, what we have here is a definition of soundness that is more general than previous work. And the key to generality is to stop thinking about the intersection of all the programs that could have produced this trace, and instead think about this single program that produced it. And even if we don't know it, we can tinker a little bit with the trace and reuse the states and get some other actual executable things out of it. We have this 3-step proof recipe that we show works really well and just is a very repeatable work. Once you've done this a few times, you can do more. And then third, we give the first proof of soundness of a predictive analysis that works with weak memory. And once we got that done, we actually did a second one. We said, oh, we can generalize this a little bit and tinker and make the predictor different, and we proved correctness of that one too. And even though there's a lot of stuff going on with weak memory, it's totally doable. So the insights here is, number one, work with graphs, work with execution graphs instead of traces. It turns out to work beautifully for predictive analysis. And then second, do this thing of borrowing the states from the execution that you saw and tinker with it, and you will get executable stuff out of it. And then just one last thing at the end. I said that the definition works for any memory model, the definition of soundness, and it does. But as it happens, our proof recipe there really seems to only work for multi-copy atomic memory models. Those are the ones where if you have a thread that issues a write, and that write gets seen by another thread, actually that write is visible to all the threads in one go. So things like TSO, ARM-V8, RISC-V, but not ARM-V7 or PowerPC. And so what we find is that as long as we're multi-copy atomic, things are great. And we're not quite sure what to do for predictors for these weaker memory models. But on the other hand, I don't think that so many predictors exist. But there's something to work on there now that we've broken the dam. So thank you.
Yeah, I'm interested in that last point that you're saying that it doesn't work for multi-copy atomic models. And the reason I ask is because like all these models up here that you have are CPU-based models, but
yeah.
I've looked at a lot of GPU memory models and they're basically not multi-copy atomic.
Yeah, that's it. I think that we need to, first of all, I think we should do more work on prediction for GPU models, and then I'm hoping that some of this can be enhanced to then work for those memory models.
Yeah, that would be really interesting.
So I think we're just at the cusp of being able to really carry this whole field over to GPUs.
Okay, cool. Thank you. Yeah.
Hi, Jens. It looked like I was back in the old days when you were teaching, right? Thank you for it looked like a tutorial. But I had one question. See, given a trace, I can have many graphs, execution graphs.
Yes.
So do you have to do anything to see that you are covering many graphs, or all? I think all the graphs is probably not possible. I don't know.
So the way I think about it is, the math doesn't come out the way I say it, but the way that we think about it in practice is that you get a trace and then you abstract it to a particular graph and then you work with that one. Could there be maybe different ways of abstracting it? Possibly, but in practice we get one and then we just take off from there. So that's the practical matter of that these predictors, in the end, you still base yourself on a run and the run produces a trace. That's the starting point.
Have you tried running different graphs? Maybe you cover them?
No, we haven't. So it's like whenever we do examples, we start with one graph and then we see what we get. So in our case here, we were simply trying to, for the purpose of this very last point of working with some weak memory models, we had some like litmus tests that we knew were challenging, and then that's usually just here's this graph that's a challenge, and then we work with that, and we don't worry about your problem.